Welcome back. This is part 11 of our workshop. So half of our instructions are done. We have our NOP, we have all of our moves, we have our halt, and then we have all of our arithmetic instructions now. Unfortunately, those are the easy ones. So now we have the remaining half, and as you can see, they're nowhere near as straightforward as the moves and the arithmetic instructions. But that is not to say that they're any more challenging. We just need to kind of think about our process maybe a little bit differently. So I'm going to start in this top half here. I'm going to save this bottom quarter, I should say, for the next episode. So we'll tackle this top quarter here. The good news is once we've implemented one instruction, we don't have to implement it each time we see it, right? Just like we with the moves, we implemented one move and we let the formula take care of the rest. Same thing with the arithmetic instructions. We implemented it once and let the formula take care of the rest. And some instructions we just don't have to worry about at all, right? Once we've implemented NOP, we don't need to implement NOP for 10, 20, 30, or 8, 18, 28, or 38. We'll just make all of our NOPs be 0, 0, and that'll be perfectly acceptable for what we're looking to do. So we do need to implement LXI, stacks, SHLD, sta, inks, inner, decker, move I, these different rotations, the DAD, LDAX. We also need to implement LHLD, LDA, DCX, and then some more rotations. Okay, so that seems like a lot, but it's not quite as much once you begin to break it all down. So let's start right with LXI. So LXI is interesting in that LXI is going to take some sort of 16-bit number and put it in a 16-bit register. Now, I know the Intel 8080 and the Z80 are 8-bit CPUs, but they are able to address pairs of registers as if they were a single 16-bit register. And that's what LXI is doing here. So what's going to happen is these are also going to follow a formula, BD, H, and SP. So we're going to need another formula to kind of figure out which one is which and to give us the correct number for whether or not we have B, D, H, or SP. So let's go ahead and start there. So I'm going to put it right underneath our register 8 function. And so this is going to return the 16-bit register offset. So again, it'll be an int. We'll call it register 16. Again, I know I'm very, let's say, naming challenged for my registers and function names and variable names. So just like with register 8, this is just going to be a switch. And if we have B, we'll return 0, right? Because using the same logic, if LXI B, comma, we're not going to worry about this D16 because that's not going to be factored into the output byte. So if LXI is a base of hex 01 and LXI B is hex 01, well, the only thing B could be in this case would be 0. Otherwise, it won't be 0, 1. Here, though, LXI D is 1, 1. So D must be equal to hex 10. H must be equal to hex 20. SP must be equal to hex 30. So we're going to take care of that. So we'll say return 0x10. For case H, we're going to say return 0x20. And then for case SP, we're going to say return 0x30. Now it turns out that when we get down to the bottom here, these registers are replicated, except in pop and push, the register name is PSW instead of SP. It's just a thing we're going to have to live with. For LXI, that last one is SP. For pop and push, that last one is PSW. So let's implement logic to make sure that we use the correct spelling of our registers for whether or not it's SP or PSW. So in SP, we can say if tokens.instruction is not equal to pop and the instruction is not equal to push, then and only then do we actually want to return hex 30, right? Because in that case, it'll be LXI. And you could just check to say if tokens.instruction equals LXI if you wanted to. I'm going to keep it this way just for symmetry of logic in a little bit. In that case, we return hex 30. If not, we're going to have to throw a new exception because we now have an error and say SP may not be used with tokens.instruction. If we have PSW, it's going to be the same thing, except instead of checking to see that it's not pop or push, we're going to check to make sure that it is pop or it is push. And if that's the case, then we return hex 30. It's the exact same number. Otherwise, we're going to throw a new exception. And we're going to say PSW may not be used with tokens.instruction. We should also have a default case. We should error out if we don't have a valid register. In fact, I like that so much. Why don't we go ahead and also add it to register 8. Okay, so that's going to take care of LXI, and then later on we'll see pop and push. So let's go back to LXI. So what is LXI? So LXI is hex 1, and then so it's going to be hex 1 plus that register offset that we just wrote. So void LXI. Again, by now we should be pretty used to our boilerplate. And we're going to want to say, okay, well, how many arguments do we have? We have 2, right? B, comma, and then some 16-bit number. So we're going to want to check that our first argument is not empty and our second argument is not empty. The action we want to take is to say that this is a 3-byte instruction, as it says so right there, and the output byte is going to be hex 1 plus that register offset. But there's one other thing that we need to do, right? This would only output 1 byte. And we did say that LXI is a 3-byte instruction. So we have to do something to deal with this 16-bit number. And so that 16-bit number is an immediate. So we're going to write a new function, an immediate function. And that will output the correct value depending on what we type in. So let's go ahead and actually write that function since we're going to need it now anyway, and that way we can say that we've completed LXI. So this will be the way that we can get either an 8-bit or a 16-bit immediate. Right, so while LXI happens to use a 16-bit immediate, you can see over here MVI uses an 8-bit immediate. So we need to deal with both possibilities. Not that any instruction will have either possibility, but we can see either possibility throughout the course of any particular assembly program. So we'll call this instruction immediate. We'll take a size, and then boilerplate, tokens, tokens, output, output. So the first thing we need to do is figure out if we have a 16-bit immediate or an 8-bit immediate. The other thing to notice is while LXI and MVI have their immediates as their second argument, every other time we see immediates being used, for example, ADI, SUI, ANI, ORI, ACI, SBI, XRI, CPI, they're all going to take their immediates as their first argument. So we also need to check to make sure and see if we're currently dealing with LXI or MVI. Because if we are, then we need to be looking at the second argument. Otherwise, we need to be looking at the first argument. So I'm going to go ahead and make a new variable there for that. Okay, so the next thing we need to check is, well, so this one's interesting. So a user, at least in like the classical CPM assembler, could put in either a decimal number or a hex number. And that doesn't sound like a terrible idea for our assembler either, but I absolutely hate the way that the old school CPM assembler did hex numbers. So the way they did it is you had to write the number and then you put an H at the end of it, which means you had to have write in and scan to the very, very end of the number to see if there's an H there to know if you're in hex or decimal, which is kind of a waste. I think the way that, let's say, for example, Turbo Pascal did it was the right way to do it. And they prefix their hex digits with a $sign. And that's the way that I'm going to do it. That way we can see a $sign right away at the very, very beginning of our string. And if we see the $sign, we know we have a hex number. If we don't see our $sign, we know we don't have a hex number. Because that also led in the classical CPM assembler having to do weird things like if you wanted your hex number to begin with a character, A, B, C, D, E, or F, you had to put a 0 in front of it and then put your hex number and then put an H, as opposed to just being able to say $sign FFFF and just being done with it. So that's what we're going to do here. So first thing we need to check is if we have a digit, and the D library has a nice handy isDigit function, which lives in standard ASCII. So I'm going to put that in, import standard ASCII. So we have our if isDigit. So the first character we read in of our argument is a digit, or the first argument we read in is a $sign, or, well, now we also need to check for if we have something like A, B, C, D, E, or F. So we can say argument 0 is greater than or equal to A. Actually, I'll wrap all these in. And argument 0 is less than or equal to F, or argument 0 is greater than or equal to lowercase a, or argument 0 is less than or equal to lowercase f. Kind of long-winded, but that kind of does get us all of our possibilities. A number can begin with a digit, 0 through 9. It can begin with a $sign, because then that tells us it's a hex number. Actually, now that I think about it, we probably don't even need to have those arguments A, because if we just say $sign, then it's a hex number. And there's no decimal number that can begin with A, B, C, D, E, or F. So look at that. We were able to simplify some of our argument parsing just by using that $sign. And that's why we use that $sign. All right, so if we have a number or a $sign, then we set a number. So I'm going to go ahead and make a new variable called number. And I'm going to say if number equals, say argument 0 equals $sign. So we're going to check, did our number start with the $sign? If it did, we want to convert this string to an unsigned short. Again, it's the largest number that we can write in. D16 is one option we have, D8 is the other option. So it's either an 8-bit number or a 16-bit number. So a U short is really the largest thing that we can write in anyway. So if our number started with a $sign, we want to say convert, not the whole string, right? This is where slices, again, can come in handy. So we want to say the argument from 1 to the $sign, and in D, the $sign is the shorthand for end of string. So what is this going to do? Well, this is going to just remove the $sign from the number and convert the rest of it, minus the $sign, to an unsigned short. If our number did not begin with the $sign, then it's just a regular decimal number, and we don't need to worry about any slicing. We can just say convert the string into a number. And that's all we need to do there. Otherwise, so this is a little deceptive where it says D16 here. This could also be a label. Maybe not specifically for LXI, but it could be a label. And so we need to deal with the possibility that any of these LXIs has a label instead of an actual 16-bit number. So how are we going to do that? Well, we can say that if we're at the point in time where we are ready to output code, as in we are currently in our second pass. So if we're in our second pass, then we are going to need to iterate over our symbol table. And if we find that symbol in our symbol table, then number is just going to be the value of that symbol. Simple as that. And that's why we have to store the values in the first pass. I'm also going to make a Boolean called found, just to show that we have in fact found this. Again, the nice thing is D will auto initialize your variables, and it will automatically initialize your Booleans to false. So we can say bool equals true here, and then we're done. Right? Because there's never going to be a case where we have two labels of the same name. So if we find our label, we're just done. We can break out of the loop. If for some reason we got to the end of our symbol table and we did not find the label that you've asked for, then that's going to have to be an error. Because that label doesn't exist in our symbol table. And by this point in pass 2, it definitely should. So we're just going to say label not defined. I think that's good enough. All right, another thing that we're going to have to do, regardless of whether or not we have a number or a label here, if we are in fact writing out code, then we had to convert that value, that number, into the actual bytes that will live in the binary. So one thing to keep in mind is that Intel 8080, the Z80 are little endian. So we can't just write the value out exactly as it is. We have to make sure that all of our values are written in little endian notation. And a quick way to do that is to say, give me the bottom half first. And then if we have a 16-bit number, then give us the top half. Let me just bit shift to the right by 8, and so they just give us that byte. And so that's why there's this size argument in our immediate function. That way we know if we're dealing with an 8-bit immediate or a 16-bit immediate. Okay, and so that takes care of LXI. And that'll take care of all of our instructions that need to have an immediate, like MVI, ADDI, ASCII, SUI, SBI, ANI, XRI, ORI, and CPI. Neat. So let's call that here for today, and we'll come back in the next episode and we'll kind of continue on with stacks, inks, inner, decker, and we'll try to get done this top quadrant of our instruction set. So let's go ahead and save our work. So implemented LXI and immediate processing. And I'll see you back here for the next episode.